I want to welcome you to another motivated statistic class. Of course, we started this material on Monday that I call principal component analysis. But before I get started today, I quickly want to make an announcement. And of course, I'm also going to put the announcement on the canvas. Um, the announcement has to do with group projects. Of course, I share with you a spreadsheet where you are expected to put the names of your group members. Situation where you have not be able to secure group members, I still want you to put your name. You can put your name on a separate side of the sheet, and of course I will assign you myself. So it is compulsory for all students, whether you have a group members or you do not have a group members, that you need to put your name. You actually need to put your name on the spreadsheet. So because what I'm going to do today is to complete the assignment. And of course, to also assign the topics automatically, randomly. Okay, each member is going to work on. We are actually moving, gradually to the end of the semester. So, like I said, make sure whether you have a group or you do not have a group members, put your name on the spreadsheet. Now, lastly, before going into the lecture, I mentioned the other time those who are interested in improving their grade for midterm one. Information about that will also be released today. If you are interested, follow the release of the information. Of course, you are going to be the one that will participate in the makeup because there's going to be a kind of proposal in the message. Follow what I put in the message. So that will be out today. And of course, tomorrow, because all exam for midterm one has already been done, I will release the solution to the midterm one exam tomorrow, so that you'll be able to know, um, you know, what you get wrong. That will enable you to compare, since you already have your booklets. And I also want to release midterm two solution before the end of the week. Okay, so I'm going to go back into principal component analysis. Let me say this. There is a kind of connection between the principal component analysis, the factor analysis, and the canonical correlation. And of course, I want you to listen, like what I've been doing since Monday is actually to walk you through mathematical and statistical architecture of the principal component analysis. But I want to first like distinguish between the principal component analysis, the factor analysis, and the canonical correlation when it comes to investigating relationship among variables. Now I need you to pay attention. With the principal component analysis, our intention is how we can reduce the dimensionality in variables or in data set. In this material, I've used an example of decathlon. We have some athletes that actually, perform more than one event. Okay, they have the combination of track event and the feed event, by principal component. If I have a lot of events, is there a way that I can just represent these variables by just few events? Maybe few variables like maybe speed, okay, or power, okay. So or maybe the kind of the strength, okay. So if I don't want to use all of that, okay, is there a way I can put it down? Okay, that is the intention in using the principal component analysis. But for factor analysis, okay, relationship exists among all these events, whether 100 meter, the 200 meter, the high jump, the long jump, the relationship that exists, okay, can we identify, what is those factors that explain the relationship? I'm going to say that again. With a factor analysis, we believe that the reason why variables are correlated, there's a reason for that. And in factor analysis, we are interested in uncovering those underlying factors that could explain athlete performance. Okay, we want to really identify that. Okay, that is the essence of the factor analysis. Now, for the canonical correlation, on the other hand, okay, is there a way we can split this event into two? Okay, into two events. You know, when you see all those events, we can classify them into track and feed. I'm going to say that again. We can classify all the events, whether 100 meter, high jump, long jump, 200 meter, and so on like that. They can all be classified into two groups, the track event and the feed event. Now, if I actually do that, which means I'm going to call the track event X. I'm going to call the feed event Y. Then what I'm going to do is I'm now going to be pairing. Okay, I'm actually going to be pairing. I'm going to form a linear combination for event under X. I'm going to form a linear combination for events under Y. Then I'm actually going to be considering a particular event in the feed event and a particular event in the track event. I will be looking at the correlation between them. What am I looking for? I'm looking for the maximum correlation, the maximum correlation of PS. Okay, so that is just the idea. Now that you know what we're talking about, I remember on Monday, I walk you through all of this mathematics aspect of the principal component analysis. Okay, but the next that I'm actually going to showcase today, I said I'm going to start from large sample properties. I've already walked you through how we can formulate a principal component. These principal components, they are actually the linear combination of the old features. Okay, I've walked you through, and let me tell you this. In the principal component, the focus is on total variance. The total variance can be written. I need to show you this. Total variance, total variance, total variance is equal. Okay, total variance is equal to shared variance. Okay, shared. Okay, the shared variance is a common variance, the common variation. So shared variance, okay, plus the uniqueness. Okay, the uniqueness is actually going to be variance that is you specific to a particular factor plus uniqueness. I needed to pay attention, okay, plus the uniqueness. When I'm talking about principal component analysis, the interest is on total variance. Okay, we actually want to identify the principal component that we explain the largest percentage of the total variance. Our interest is not on the shared variance. Our interest is not on the uniqueness when we're talking about principal component analysis. But when I'm talking about factor analysis, we are not interested in total variance. Factor analysis focuses on shared variance, not total variance. Okay, now, uh, if you now that you understand the composition, I want to talk about last sample property. What is the meaning of the last sample property? If I have opportunity to have a large sample size, okay? If I have a random variable S that are features that follow multivariate normal distribution with a mean vector of this guy, and this as the variance covariance, and there exists what I call the eigenvalues of the covariance. The eigenvalues are the variance of each of the principal component, where the lambda 1 is the largest variance. The largest variance actually, is the contribution of the first principal component. Now, what happened as n tends to infinity? When I say large sample property, I'm actually focusing on situation where the sample size is sufficiently large. That is where the number of observation is sufficiently large. Now, I need you to pay attention, situation where that happen, okay, with the distribution. Now, what are we focusing on here? Please pay attention. Our estimator here is the eigenvalue. The lambda cap is an estimate of the eigenvalue. The lambda here is the average of that particular estimate. Okay. And of course, if you want to rewrite, please pay attention. If you want to rewrite this, if you want to rewrite this guy, it is the same as the cap, okay, minus the mean. This is the mean. The one without a cap is the mean divided by 1 over square root of the sample size. Okay. And another way to write that is to write it this way. Now, you know what I'm trying to say? If this guy is the estimate, this is the mean of the estimate. What you have here is the standard deviation of that estimate. But you know what I'm focusing on now? I'm focusing on the distribution of the whole thing, the distribution of the difference. The distribution of the difference between an estimate of the eigenvalue and its mean. Then we said it followed normal distribution with a mean of 0, okay, and the variance of this guy. Please pay attention. So what we're seeking now, okay, because why are we interested in the distribution? Because if you want to conduct a statistical inference like testing hypothesis or constructing confidence interval, you actually need the distribution of that. So I'm seeing the whole of this guy now as an estimator. I'm going to say that again. Since lambda cap is an estimator, a function of an estimator is an estimator. The whole of that is an estimator. Okay, it's an estimator because it's going to vary. It's an estimator, is going to have a mean of 0, and it's going to have the variance of 2 lambda squared. Now, the same thing also applicable to this guy. But let me tell you this. The distribution is not normal initially. I'm going to say that again. Distribution is not normal initially. But what makes the distribution to be normal is when the sample size is sufficiently large. So what we're trying to talk about here is when the sample size is sufficiently large, we expect these two estimators to follow normal distribution. Okay? And if they follow normal distribution, another implication is that the two estimator, I need you to pay attention. Okay, now this guy and this guy, they will be independent. They can only be independent if the n is sufficiently large. That is what that information is talking about. Okay, now moving away from there, I want to talk about principal component analysis in practice. Now, which is we're seeking solution. We have that I said, we have different kind of approaches that can be used. Do we want to go by way of a covariance structure, or we want to go by a way of correlation structure? Now, this is to invest, this is also let you know that if I'm seeking PCA solution, I can go by way of a singular value decomposition. And I told you the other time, going by way of a singular value decomposition, we're actually going to decompose a matrix into three pieces of matrix, which is this guy here. We are the first one, we're actually going to call it something. The one in the middle is a matrix, and the other one also a matrix. So it's like here, we are actually going to use the idea of matrix decomposition. Okay, now the XVD. So this actually denotes what I call the SVD. Okay, now I think I explained that on Monday. Okay, now we have what we call the right singular vectors of the mean-centered. We have the eigenvectors of the covariance. And I remember on Monday, I walk you through how you can actually, set up your sample covariance matrix. Now, what I'm trying to tell you now, if I set up my sample covariance matrix and I have this guy, then try and decompose that into three pieces. That's what that guy is trying to say. I have a sample covariance matrix. Of course, I show you on Monday what SC represent. SC, you get that from a data matrix by centering, where you subtract the mean from each and every data point within the column. And after that, you find the transpose of that, you multiply by itself, you divide by n minus 1. That gives you a sample covariance. A sample covariance is a matrix. Then if we decompose that, we split that into three. Okay, when we're using the idea of a singular value decomposition. Okay, so this is to tell you, okay, this guy in the middle here is the eigenvalues. Okay, this guy, eigenvector, this guy, the transpose of the eigenvectors. I'm going to say that again. You have the eigenvectors multiplied by the diagonal. The diagonal is the eigenvalues, which are the variances of the principal component multiplied by the transpose of the eigenvector. Now, I take another not to waste our time. I'm actually gonna walk you through an example, and I need you to pay attention. This example is coming from men's Olympic decathlon data from 1988. We got 34 athletes, and these 34 athletes, okay, they have participated in 10 events. Each of them participated. Let's say, has anybody watched an athlete uh, that performed a decathlon before in Olympic? Has anyone here understand what we mean by that? Okay, I know there are some athletes in Olympics. Some of them do track events only. Some of them do speed events only. We have some athletes that do the combination. Now, the decathlon has 10 events, 10 events, okay? And there are some athletes that participate in all the 10 events, and they're going to score them at the end of the day to know the best among them. Now, in 1988 Olympics, we have 34 athletes, and they participated in 10 events. But why do we want to use the principal component analysis here? Please, I need everyone to pay attention. Okay, so I need everyone to pay attention. Why are we interested? Do you know on this same data, okay, I can also use a factor analysis. I can also use a canonical correlation. But my intention using a principal component is different from my intention using a factor analysis. And of course, it's different from my intention using a canonical correlation. And I need you to pay attention now. Now, my intention here is instead of using 10 variables, is there a way we can prune this down to few numbers of variables instead of us to base this on the performance in 100 meter, the performance in long jump, the performance in high jump? Can I have some few variables like where the first one may be representing endurance, and maybe the second one is going to represent speed, okay? And maybe the third one is just going to represent the general athleticism. Okay, instead of me to have the whole 10 events, okay, can I prune it down? Okay, just using maybe less than 10 to explain the performance of the athlete. So the essence of using the principal component analysis here is to reduce the dimensionality, okay, in this data set. But while we're doing that, we actually want to settle for fewer variables that can explain the largest variance. Does that make sense? Okay. If you don't understand, please ask question. Now, I said there's a overall the Cartelian score. Now, this is the data set, okay? And these are the names. Please pay attention. These are the names of the athletes. I'm talking about 1988 Olympics. Okay, we already have the score. They've participated. We have the record. Okay, you can see the same athletes run 100 meter with 11.25. The same athletes in a long jump 7.43. The same athlete. So when you look at it in a row, you are referring to a particular the score of a particular athlete in each event. Does that make sense? And if you look at, if you look at here, you're actually going to see a score. Okay, that would be the total score for that particular athlete after participating in all events listed. If you look at it column wise, you are only focusing on a particular event. Does that make sense? Now, this is going to act as a data frame right now. This is our data frame. Now, it means based on this, you can actually set up your data matrix X. Your data matrix X. Now, I need you to pay attention. Please pay attention. We actually need to do some data wrangling. We actually need to, prepare our data, in a usable format before the analysis. We want to make sure the scales are the same. We also, because I need you to pay attention. When you talk about running events, okay, the running event, the lowest value in the running event represent the best. When you run 100 meter, the best is somebody who run that with very short time. But when you look at the other event, like a track, I'm sorry, like a feed event, high jump, long jump, okay, the more the values, the best is a candidate. So, which means when you look at, please pay attention. What I'm trying to talk about now is very, very crucial. We don't just analyze data set. We have to analyze data set with common sense. Common sense, if you take a look at all the variables here, they are not, in the same scale because some, when you look at the track event, the best, okay, scores are the lowest. But when you look at this, the feed event, okay, you're actually going to see that the bigger the numbers, the best is in the performance. Now, I need to do something to make sure they are all in the same scale. And this is what I did. I actually multiplying -1 by all the track. Take a look at what I've done here. Okay, the -1, I'm multiplying that by column 1, column 5, column 6, column 10. Okay, you can see 100 meter now is negative, 400 meter hurdle. Why am I multiplying that why am I multiplying by -1? Because they are not in the same state with the feed event. Okay, so right now multiply by -1, then I realize they are in the same state. Okay, now the next now, what I'm doing right now is what I actually call, pre-processing approach, where we're trying to clean our data, where we're trying to make sure, the scale in the data set is the same. If you don't do that, there's possibility that a particular variable could dominate the others. Now, after that, the next that I actually want to do is I will go ahead to construct my PCA. Okay, I want now doing the PCA, I want to start with the covariance matrix. Okay, the covariance matrix. Okay, so the covariance matrix. Okay, now I need you to pay attention. I actually, if you take a look at the coding now, okay, if you take a look at this, okay, look at that, and it means I want to generate my PCA from the data frame, okay, using the covariance matrix. And after that, I'm actually going to show you what we're going to have. Now, if you take a look at all of this, if I really want to recall, my results. But before I can actually use the covariance, I actually believe that they are all in the same unit. Okay, all the variables are in the same unit. Okay, so are they all in meters? If some are in meters, I know 100 meters, 110-meter hurdles, 200 meters, all of them are in meters. If they are all in the same unit, I can use covariance. But if they are not in the same unit, then I will use correlation matrix. The correlation matrix is a correlation is a standardized covariance. Now, if you take a look at what I have here, I'm displaying two results: the plot of covariance and the plot of correlation matrix. And right now, I'm only using two principal components: principal component 1 and principal component 2. I say PC1 loadings and PC2 loadings, maybe I'm only using PC1 loadings and PC2 loading because they explain the largest portion of the variance. We got a threshold that we can actually use to determine the number of principal components. Okay, I'm going to show you what we use. We can use a screen plot. We can also use there's a particular threshold that, okay, at least 80%. Okay, maybe the first two principal component explain at least 80% of the variance. The belief is there is 100% variance, which is the total variance. How much of this variance, okay, can be explained by the principal component that we choose? Okay, at times we could say, okay, if the first two cumulatively, if the first two principal component cumulatively can explain at least 80 something percent of the variation, okay, then I'm actually going to choose them. Now, what you see right now here is when I use the covariance, okay, constructing the PCA using the covariance. And using the covariance, you can actually see javelin, discus, shots, they run the 1005 and so on, like that. And you can also see that way because whether you use the covariance matrix or you use the correlation matrix, the two principal components that you come out with, each of them is still going to be a linear combination of all the independent variables. And we said linear combination, which means we're actually going to have something that we call loadings. Loadings are like weights. The loadings, we're going to have a loadings for each of this event. Okay, the loadings will tell us the contribution of old variable to the new transform principal component. Okay, now this is the correlation of PC score and overall Decathlon score. Okay, if you look at that of the correlation matrix, it's looking like a straight line. Okay, but if you look at the covariance, you can see the relationship they have. Okay, now I can decide to round all the way. If you take a look at what I have here now, I'm having the score and the PAC. This is the one for the covariance, the one I derived using the covariance, and the one that I derived using the correlation. I round them to 3 decimal places. Now take a look at this. These loadings, these are called loadings that will give you the contribution of each of the initial variables. Okay, that is when you fit covariance. And when you fit correlation, okay, you're actually going to have this. Okay, we run that to 3 decimal. I've told you the condition under which covariance will be appropriate when all the variables are the same unit. But when they do not have the same unit, okay, you have to use correlation. You can see we have different results. Okay, for the first one, we have a 0.214, but that was under covariance, but under correlation it was 0.991. Okay, so I need you to pay attention to that. Okay, now like I said, um of course we know the PCA is actually used to reduce the dimensionality. It's a dimensionality reduction technique. And of course, in practice, we do not know the number of principal components in advance. So that will be determined during the course of experimentation. Okay, that will be determined. So I said, in some cases, possible feasible value may be known a priori from theory or past research. At times, depending on the area of research, okay, there's possibility. But do not allow what you know from the past research, to actually override, your analysis. You still need to conduct your independent analysis to figure out what is the optimal number of principal component that is actually going to do justice explaining the most variance. And I said, in other cases, we need to choose some data-driven approach to select a reasonable number of components. Like I said, it should be data-driven. Data-driven means what I'm going to get from my data. Okay, I'll figure it out from my data. And one of the tools that we use is what we call screen plots. Okay, we call screen plot. So the screen plot will show us the variance that is explained by each component. Don't forget, the variance that is explained by each component, okay, is what I call eigenvalues. Eigenvalues. They are the variances of each of the principal component. If you take a look at the screen plot right now, what do you see in the vertical axis? In the vertical axis, you can actually see the variance. In the horizontal axis, you see the component. We have 10 components. We're still talking about the example. So take a look at what we have now. Now you can see that when you started, okay, when you use the principal component 1 all the way, okay, you see what is actually going on. It gets to a point that it converges. Look at that. So the point at which it converges is what we actually going to look, what we're going to identify. Like I said, we look for the elbow, okay, just like an elbow, okay. You see, we look for the elbow, okay, of the plot and point where line bends, okay. We want to point where the line actually bend. Of course, at times this may be kind of confusing using a graphical approach. We got some standard tests that can be conducted. That was why I said could do formal tests on derivative of a screen line. But common sense approach often works fine. Okay. Now, if you take a look at what I have here, if you take a look at what I have here, it's trying to say that using four components and above does not really add any significant improvement to the explanation of the variance. That's what that guy is trying to say. Okay, it doesn't add any significant improvement. Okay, and of course, if you take a look at what I have here, okay, this is pointing to the fact that I think the first two may actually do the job before we start having the able. Okay, now, whether you use a covariance matrix or you use a correlation matrix, you can decide on what is the optimal number of principal component that is actually going to work. You can draw a screen plot for the two, which is what I'm showing now. Okay, this is the principal component analysis. I want to quickly use my time to go into, I want to start the factor analysis. Now, of course, the idea behind the principal component analysis is to identify fewer dimensions. How, we learn how we are able to project, higher dimension into a lower dimensions, okay, without losing a lot of information. And we're able to identify, the first few components that adequately did the job. But I want to welcome you into factor analysis. The idea behind factor analysis is not about explaining the total variance, but it's about identifying what are the hidden factors. When I say hidden factors, something that we have not observed that explain relationship between variables. The event that we are talking about in Olympics are related. 100-meter is related to 400-meter. Okay, they are all related to themselves. But we want to identify some factors that could explain that. And that is why the interest is not on the total variance, but the interest is on shared variance. Okay, now I'm going to walk you through all of that. Let's talk about background. You see that? We assume that the covariation structure among the set of variables can be described via a linear combination of unobserved. When I say unobservable latent variables, I mean hidden factors that could explain the reason why the variables are dependent in the first place. Now, let me also say this. Principal components perform a role of dimensionality reduction. Factor analysis also perform that role. But let me tell you this. In principal component analysis, we are trying to reduce the numbers of features, okay? But in a factor analysis, after we have identified the hidden factors that explain the reason why the features the features correlate, we also want to reduce the numbers of hidden factors. Okay? We don't want a situation where the number of hidden factors will be the same as the numbers of features. We don't want that. And that was why you see this. If R, okay, is the numbers of the hidden factors we have identified, that numbers of hidden factors should be less than the numbers of the original variables. And this is by this we say that factor analysis also perform dimensionality reduction technique. Role. Now there is interpretation because identifying factors that explain features, then we mean that we are seeking an explanatory goal because we actually want to investigate how some factors explain a particular feature. Okay, and that's what we mean. Then from there, we can actually talk about testing theory. Let me tell you this. Whenever you are seeking an explanatory goal, you will test hypothesis. I'm going to say that again. Whenever you are seeking an explanatory goal, a causal goal, then you need to test a causal hypothesis. And that's why I said determine if hypothesized factor structure fits the observed data. Okay, now I think I've explained the difference between the two. Please pay attention to this. I need you to pay attention to this. Look at that. The two of them actually work on linear combination, but they do that differently. The factor analysis assumes that statistical model that describe variations or covariation in observed variables that occur via linear combination of the latent variables. The linear combination of the latent variable. The latent variables are the hidden factors. But in the principal component analysis, that find uncorrelated linear combination of observed, not unobserved, of observed variable that explain maximum variance, which means in principal component analysis, we are not interested in the hidden factor that I explained, the variations among the variables. We're not interested in that. So know the difference between the two. Okay, now the factor analysis refers to statistical model. Why is it a statistical model? Because in a typical statistical model, we're looking at the effect of a variable on another variable. So in that model, you are looking at the effect of some hidden factors on the original features. That's why it's a statistical model. Okay, but why principal component refer to the eigenvalue, the composition of a covariance matrix. The principal component will actually decompose the covariance matrix into pieces. And those pieces, one of that will be eigenvectors. And the eigenvectors is actually going to be called loadings, which is going to be the weight, which explain the contribution of, in a particular principal component, it explains the contribution of the original features. Now, where I'm going to start on Friday, I'm going to start because in statistics, if you want to talk about model, if you want to talk about, if you are seeking an explanatory goal, okay, in factor analysis, we're going to be seeking an explanatory goal that we need a typical statistical model. Okay, we need a typical statistical model for factor analysis, which is where I'm actually going to start on Friday. You can see we have a specification of model, but we do not have that in the principal component analysis. In the principal component analysis, we did not specify a model with errors No, because we're not interested in a particular variance. We're interested in the total variance in the principal component analysis. But in the factor analysis, we are not interested in the total variance. We are interested in a shared variance. And that is the reason why we need to have a model specification. This is where I'm actually going to stop today. Like I said, if you have not put your name on the spreadsheet for the group project, whether you have a group members or you do not have a group members, make sure you put your name on the spreadsheet. Okay. Now, if you don't have a group member, do not put your name where a group members have put their names. Okay, there's a lot of space in a. So I will automatically assign those students that have not secured group. Today, I'm going to make an announcement where I will randomly myself assign areas the group is going to work on. It's not going to be a student that will decide, oh, this is the area I want to work on. But my motive is make sure you understand all the areas we've done because you can be randomly assigned any of the area to work on. Make sure you all stay safe and have a lovely day. Bye for now, everyone.